Welcome everybody to this lecture on room acoustics. And I appreciate that so many have come through this snowy weather we have today. But in the next hour or so, I should like to give an overview of the room acoustics with some view to waves and particles. Here is the outline. First, something about modes and diffuse and non-diffuse sound fields, particles, diffraction, scattering, curved surfaces, some quite heavy stuff maybe. And then we come to the computer modeling with some examples addressing the speech or the music in rooms. But we start with Wallace Sabine, who could be said to be more or less the father of room acoustics as a science. It's more than 100 years ago now that he started to look into room acoustics and to came up with the concept of reverberation time. And in those days, they didn't have the equipment we know today. So I just should like to mention how he has described in his papers the technique he used to actually measure reverberation time in rooms. And on this figure, you can see a special setup with 4 identical sound sources, each sound source consisting of a number of organ pipes. And these organ pipes could be controlled, turned on and off from the measurement position. And the principle he had derived was that he could compare measurements with 1 organ pipe or with 4 identical organ pipes in different positions. We also know today that if we have 2 identical sources, the sound pressure level in the room will go up by approximately 3 decibel. And with 4 identical sources, it will be about 6 decibel. And what he could measure then was the decay time until the sound had reached the background noise. So he used his own ears, listened to the sound, made the stop of the organ pipe, then started to measure the time very accurately, and then he could stop the time measure when he couldn't hear the sound anymore. And with 4 organ pipes instead of 1, of course he could hear the sound a little longer, and the difference in time corresponded to a decay of 6 decibel. So he just had to multiply by 10, and then he had the decay for 60 decibel. And it was amazing how accurate he actually could measure with this technique. I guess he has trained a lot with his ears. But about sound as a wave, I will here show also some historical pictures from around 1929. I have got this picture showing the use of a water ripple tank to investigate the wave diffraction and reflection in a 2D scale of an auditorium. But the modes in a rectangular room can be described as 3 sets of cosine functions, where we have the room dimensions Lx, Ly, Lz, and we have also the natural numbers Nx, Ny, and Z that indicate the mode number. So for each mode, there is assigned resonance frequency or a natural frequency, and that can be calculated from this equation here in the bottom of the slide. For some examples of the mode numbers, the three ends. You can see up here the series of normal frequencies starting from 25 Hertz as the lowest one in this room. And if you look at the frequency response, it is usually possible to identify the peaks in the frequency response as corresponding to certain modes in the room. Well, sometimes it can be difficult because the modes can overlap in frequency, and if we come higher up in frequency range, they get closer and closer, and it becomes more and more difficult to separate. And what contributes to that is that each mode actually has a certain bandwidth. So when the lateral frequencies get closer, they tend to overlap more and more. And for that, well, to describe that, we have the modal overlap, M, which is, well, the bandwidth multiplied by the modal density. And here is very convenient to introduce Schroeder's limiting frequency, which is, well, an approximate guide for which frequency distinguish between the low frequency range, where we can identify the modes, and the high frequency range, where they are smoothed together. And you can see the equation, a simple equation where we just have reverberation time and volume in the room. So the transfer function above this Schroeder frequency can be showed here in two examples. And again, this is taken from an old reference, but today everybody can do the same experiment, just to have a sine sweep slowly, in this case from 900 Hertz to 1000 Hertz. And if you do that in a reverberant room, you will have the upper curve, where you have a short distance between the peaks in the transfer function. But if it is a dead room with short reverberation time, there will be much longer span between the peaks. And approximately the difference between the peaks is 4 divided by the reverberation time. Well, I would not recommend this as a new method to measure reverberation time, but it's just that there is an approximate well, correlation between the reverberation time and how the transfer function will look. So the number of modes can be calculated from an equation like this, where the most accurate one takes the volume and the surface area and the total H of the room into account, but a quite good approximation just takes the volume into account. And you will see that the modal density increases with the square of the frequency. We just put that aside now, and then I will refer to it again in a minute. But now I will take a new start and look at the sound in the room as the propagation of particles. Well, an obvious model for that has also been used in the early days to investigate room geometry. Here is used the light from a source, and the source has some slits, so only parts of the light can escape and be reflected from the room model. And then we have, when we look at reflections, it is possible then to look at the number of reflections arriving to the receiver from points which are coming as, well, I could say like images of the real room. So we have image sources in the image rooms surrounding the real room. And from that model, it is possible to calculate the reflection density. That means the number of reflections within a short time interval. And you can see that also depends on the volume, but here as it depends also of the time squared. So it is quite similar to the modal density, which depends on the frequency squared, but here we are working in the time domain, but there are very, very close similarities between frequency and time domain. That means that if you look at the arrival of reflections as a function of time, in the beginning they come very separate, and we can usually distinguish every single reflection, and maybe we can sometimes also trace which surface creates the reflection. But after a certain time, it becomes quite impossible to separate single reflections. They merge together, and we don't have today a well-established limit for this transition between early and late reflections. There has been papers published also recently. What I have put on the slide here is a little older suggestion from Professor Kramer that the time can be approximated as 2 times the square root of the volume. If we look at reflections in terms of reflection order, then this is a very interesting figure produced by Professor Kudruf, where he shows that the first order reflection will contain a big part of specular reflected sound and normally a small part of scattered sound. But if you go to the second order, it is a larger part which is scattered, and the higher reflection order you go to, the more of the energy will be scattered energy, and very little will be specular. Specular means that you can trace the energy in the reflection through the different reflecting surfaces back to the source, but that is impossible with a scattered energy. So you can here talk about a transition order where you have a transition from mainly specular reflected energy to mainly scattered energy. Well, this is a small experiment where we have just the direct sound of a hand clap, but the source and receiver are located in well, a room to be built now. So I will build it first by one wall. And this wall creates a reflection. So every sound arriving has, well, a kind of echo. If we now have more walls, you can hear a series of echoes because 2 of the walls here are parallel. So there will be, in principle, an infinite row of image sources creating all these delayed reflections. And finally, if we close the room, we have 6 surfaces. So now we just hear a very reverberant space. We don't hear the flutter echo anymore because there are many other reflections interfering. All these sound examples are made with ODEON simulations, of course. It is here shown that we can represent the sound reflection with a ray, and following reflections from surface to surface in the room, there will be different distances between the reflections, and then it's also well, a very old knowledge in room acoustics that we can calculate a mean free pass, which in a three-dimensional room will be 4 times the volume divided by the surface area. After each reflection, the sound will be reduced in the energy by a factor 1 minus the absorption coefficient. For the beginning here, we can assume the same absorption to all surfaces. If you do that, it is possible to set up some equations to calculate the sound energy after a number of reflections, n. And then we can say that corresponds to a time, after a time equal to the reverberation time, there will be a decay of the energy to 1 to the millions of the initial energy. And then we can derive an equation for reverberation time as a function of mean free pass and the mean absorption coefficient. And that result includes the natural logarithm. However, for absorption coefficient not being too big, say less than 0.2 or 0.3, then we can use the approximation shown here in the frame. And these 2 equations I should like to emphasize here as general equations of reverberation time. Much more general than the well-known Sabine equation, for instance. Because the Sabine equation, it will be appear here in this table in the second row in the right column. You have the Sabine equation, and that includes the assumption of a 3-dimensional sound field. But in many rooms, the sound field may be more like a 2-dimensional field, or maybe even 1-dimensional if you have absorption on several surfaces and then a few hard surfaces. And for 2-dimensional or 1-dimensional sound fields, you have very different mean free pass, which leads to very different reverberation times. Let me take the most simple example. You have just 2 parallel walls, and the rest are absorbing or maybe the open space. In that case, the mean free pass is simply the distance between the walls. Of course, the sound is traveling forth and back between the 2 reflecting walls, and that will create a longer reverberation time that you would expect if you use the usual Sabine equation. But you have all the equations here, and the Sabine versions, you could say, are in the right column, the most simple equations, but you also have the version with the logarithm included, which can be used for more absorbing cases, and they are called the Eyring equations. So these are the special cases of a 3-dimensional sound field, the quite well-established equations of Eyring and Sabine. This will lead to the final part of this discussion about particles and waves in rooms, because I would now like to show what happens in a simple case of a non-diffuse room, namely a rectangular room where we have the ceiling very absorbing, absorption coefficient of 0.8, but floor and the walls are quite reflective, absorption 0.1. And then we can calculate the mean free pass, we can calculate the reverberation time according to Sabine, it's 0.76. According to Eyring, a little shorter. But the really interesting results are if we now realize that there could be a two-dimensional sound field just propagating between the hard walls, then we have a much longer mean free pass and we will have much longer reverberation time for these two-dimensional reflections, namely more than 4 seconds. And finally, we have shown here some examples of one-dimensional reverberation times between the end walls with a distance of 20 meters. You can see we will have reverberation time around 8 seconds. So it's a wide range of reverberation times that we can have at the same time in the same room. And what we will experience in the measurement will be some kind of mixture of all these different decay processes. And that's why we can also get quite different results depending on source position and microphone position. And it's very important to average with a number of positions. It's a very complicated mixture of very different decay processes. And this is something I really want to emphasize, because I think very often we tend to forget about these things. We just rely on the Sabine equation, and for instance, if it doesn't give the same result as we measure, then something must be wrong. And also, if you have a different result from the computer simulations, well, some users may say something must be wrong in the computer model because we still rely on Sabine. But now I have given you a strong warning. I think Sabine is not just one solution to the problem. And actually, I could say this example of non-diffuse rooms is a very strong reason for why we have developed a room acoustic simulation software like ODEON. Now I will say something on the surfaces and the reflections, how they are created from the surfaces. And a very interesting but also difficult thing is the scattering. And the scattering coefficient, which has now been established in ISO standard. So there is a consensus about how to describe this phenomena, and there's even a measuring method, as I will mention. The scattering coefficient is the ratio of reflected energy in non-specular directions. In other words, the ratio reflected in the specular direction, if it was an ideal plane surface with no scattering, then this ratio would be 1 minus S. And then I have tried to make some simulations in ODEON, and actually using the rectangular room with dimensions 10 by 20 by 5 meters, and with absorbing ceiling and all other surfaces reflective. And here the result with quite low scattering. That means I have assumed the surfaces, particularly the walls, to be quite smooth. And in that case, the result shows that we will have decay curves, as shown in the left lower part of the graph. We will have decay curves which are not straight-lined. They are combined from the different decay processes as I described. So they are bent. And the further down we go on the decay curve, the more it will be dominated by one-dimensional decays with a long reverberation time. That also means that we will have quite different results depending on which part of the decay curve we use for the evaluation of reverberation time. According to the standard, we can choose the 20 decibel or the 30 decibel evaluation range, and you can see on the graph the difference between the red and the yellow bars here, that there is some difference, and the T30 values are clearly longer than the T20 values. Reverberation time here in 1 kilohertz is calculated to about 1.7 seconds. We just remember that for a moment, because now I will change the scattering of the room. Now I will make a quite high scattering, 0.5, and then at once things change. Reverberation time goes down to 0.7, about half of the value before. Decay curves becomes almost straight lines. We have very little difference between T20 and T30. So with scattering on the walls, we suddenly have a quite different result, and actually a result which are closer to the Sabine equation. If we increase scattering further, total scattering, that makes no difference. In other words, scattering is very important in the lower range, from 0 up to about 0.5 or 0.2. But if we go further, about 0.5, then it is virtually like having total scattering. The sound decay in non-diffuse rooms I have now explained, and the uneven distribution of the absorption means that the decay process will be very dependent on the scattering in the room. Now I will look more into the single surfaces and diffraction phenomena. So we just have a single reflector here, and the source and the receiver, and we introduce the characteristic distance as well, some kind of average between the distance from source to reflection point and distance from the receiver to reflection point. And actually this kind of average is quite common in acoustics, and it is called the harmonic average. A nice name for it. And I have worked on this some years ago using the Holger-Rindel approximation, which means that we will establish a coordinate system with origo in the point of reflection, and set up some equations which I will certainly not explain in detail here today. But what is very nice, I think, is that the mathematical equations, which looks terrible, they can actually be interpreted graphically in a figure like this one, which is called a conus spiral. We have two parameters, C and S, which are called the Fresnel integrals. And if we have a certain reflecting surface, rectangular surface shown here, then the edges are the important things. So if we have, for instance, an infinite large surface, which means that U1 goes to minus infinity and U2 to plus infinity, then we go from the center of the two spirals, as shown in the red line, and the length of this line is a measure of the amplitude of the sound reflection. That means if we go with different through different frequencies, we can travel through this spiral and then explain why we have different sound pressure reflected. I will give you some examples in the next slide, but the infinite reflector is taken as a reference. So we take this as a reference, the red line here, And then we can introduce a finite size reflector. And again, we can solve the problem using these Fresnel integrals, where we have also the wavelength included and the distance to the edges. And then we have results like these two examples I have shown on the same graph. In the upper example, we have the reflection point in the center of the reflector. And in the lower example, we have a reflection point at the edge of the reflector. And you can see the end points on the Cornu spiral. It is approximately the same size of the reflector or of the vector. That means that we have approximately the same amplitude of the sound pressure reflected, but the position in the Cornu spiral is very different. If we increase the frequency, it means that we will travel further out in the spirals, and now we have a higher frequency, and you can see what happens in the upper figure. Both endpoints have now moved along the spiral, and we have got a much longer vector, the green one, corresponding to a much stronger reflection. In the lower example, we still have one point at the edge that doesn't move, but the other one is moved further into the spiral, and we have come through some of the first fluctuations. So the figure to the right explains how sound is reflected from a finite size surface, and we can see that at higher frequencies there will be fluctuations within a few decibel coming from the interference between the opposite edges. But at lower frequencies there will be just a simple decrease of the reflected energy. If the reflecting object is small compared to the wavelengths, there will be very little energy reflected. That is the message, I could say, from this. Then we have here some experimental results where this theory was compared to measurements in the anechoic chamber, and quite satisfying agreement. There were made a lot of experiments to establish this model. The fluctuations are explained at the high frequencies are not really important because there are many other things creating similar reflections in a room. The important thing is that below a certain frequency the reflection will be attenuated simply due to the finite size of the reflector. And this limiting frequency or design frequency I have suggested in another paper a long time ago to be calculated from this characteristic distance, including distance to source and receiver, and the surface area and the angle of incidence. And well, this has also been taken into ODEON in the calculation methods. But I can show you here some examples of the directivity of reflections. Another thing which could be worth looking at. And here I have measured results from Mendel Kleiner, published in 1996. The upper one is a rectangular plane surface giving a distribution of reflection with some side lobes, and the lower one is a reflection from a diffusing surface. And actually we can use this principle with the theoretical reflection model to find that the reflected sound intensity can be described as mathematical functions which are the type sinus x divided by x, and where this x contains the wavelength, the size of the panel, and the angle of incidence when compared to the angle of reflection. If alpha 0, beta 0 are the angles of incidence, then alpha and beta represent the angle of reflection. And then we can calculate the directional characteristics of the sound reflected from a surface. And depending on different angles of incidence, you can see that the sound will have a certain spread in different directions, particularly at low frequencies. So, for example, if the dimension of the panel is 0.88 meter, and we look at a low frequency like 125 hertz, it corresponds to the curve Ka1. I can just go back. Ka1 is the yellow one. Now a little more about the specular and diffuse reflections. I have mentioned the scattering coefficient, and it is defined in this ISO standard that came a few years ago. And in this standard is defined or described a measuring method. And interesting enough, it is very common to measure the scattering in the scale model of the actual structure. So this is maybe the first measuring method standard which addresses scale models. But the result is very useful for computer models. Here are just some examples of test objects. They have to be circular for this kind of measurement, because measurements are taken with different rotation of the test specimen. Scattering coefficient can go from 0 to 1, and typically increasing with frequency. You don't see much details on the graphs here, but it is more or less the same story for all test specimens, that there will be an increase in the scattering, and at which frequency it is scattering more than a certain value. That depends on the size of the structure or the roughness of the structure. But for the computer model, we have then addressed both the roughness and the diffraction due to finite size. So that means you can talk about a combined scattering coefficient which takes both effects into account, both the finite size and the roughness of the structure. And the finite size is taken from what I have shown earlier in the diffraction model for reflectors. There is a certain attenuation at low frequencies, and the attenuated sound is still reflected, but in different directions. In other words, the attenuated sound at low frequencies is some kind of scattered sound, and that is exactly the energy we need for calculating the total scattering effect. Let me show you some simulations here in the computer model, where we have a small surface reflecting, but we move the sound source in two different positions. In the closed position, the reflecting surface is relatively large. That means the characteristic distance is quite short compared to wavelengths, and it will be a very efficient reflector. But in the long distance, the reflecting surface creates much stronger diffraction, and it's mostly scattered energy from this remote position. The scattering coefficient is applied in the computer model, but when it is necessary or not to apply it, then that depends on the degree of detail in the model. As an example, I have taken this music studio, which has some scattering elements in the ceiling and one of the walls. And we can include all these details in the model as in the upper picture, or we can simplify the model with plane surfaces, and as in the lower picture. And in this case, with simplified surfaces, we need to assign a higher scattering coefficient to compensate for that. So here I'll show you what happens in this simplified model without any scattering. And this is not a very realistic simulation of sound reflections. However, if we include a scattering coefficient, in particular a high scattering on the left side wall and on the ceiling, then we will have a result which is more close to the real behavior of sound. The alternative is this one. Here we have the same scattering coefficient, a quite low scattering on all surfaces, because here the geometry will deal with the scattering effects, here coming from diffraction of the finite size diffusers. Curved reflectors are particularly interesting because they have the ability to scatter the sound or to focus the sound, depending on whether they're convex or concave. And a simple geometrical analysis of this has led to an equation which is shown here. It can show that the attenuation due to curvature of the surface depends on the radius of curvature r, of course. It depends on the characteristic distance, again, the same as before, distance involving the distance to the source and to the receiver. And then the angle of incidence, theta, is included. The radius of curvature is here considered either positive or negative. It is positive when we have a convex spreading surface, and it is negative if we have a concave, that means a focusing surface. And you can see clearly in the graph that the focusing, the strong amplification of the reflection will happen when this parameter r asterisk divided by r cos theta, when this is equal to 1. Attenuation will appear for all values of the convex reflector and also for the concave reflector if we increase this parameter beyond a factor of 2. Then it will start to spread the sound. And this is typical what happens if we have a dome with a small radius of curvature in the church, means it could be high above the ceiling. Then there will be focusing effects in the dome, but when the reflections continue and reach the floor, they have been spread again. So concave reflectors need not to be very dangerous if they are at sufficient distance from the source and receiver. Computer modeling. As introduction to the computer model, I have shown a figure from a paper by Schroeder in 1970, one of the very early suggestions of a computer model, which actually is very efficient also today. I will explain in a minute. But first, the most simple computer model takes the image source method into account, and then it's possible with a computer to calculate the position of the image sources and then create the reflections. And that works fine with rectangular rooms, and it doesn't work very well for other rooms, more realistic rooms. And the reason for that you may see here in the right-hand figure. If you have just two surfaces reflecting, not meeting in a right angle, then you can have different image source points, first order and second order image source points. And the second order image source points can be, depend on which position you actually have of the receiver. In other words, there will be a rapidly increasing number of possible image sources you can calculate, and there will also be a rapidly increasing number of image sources which are not valid. So most of the calculations will be in vain because only a few of them actually turn out to represent a real possible reflection path. If you have a different receiver point, then it could be some other image sources that are the valid ones, but the calculation time increases really exponentially with this kind of model. So it is not so useful for room acoustic simulation, especially in the concert halls and similar complicated shapes. Well, here you can see image sources created in a simple model and the reflection path corresponding to each of the image sources. But particle tracing is quite closely related to ray tracing, which I will also explain. But particle tracing means that you have a point source and you let particles escape in different directions and then follow the particle from one reflection to the next. And each particle is assumed to carry a certain acoustic energy, and then the energy is reduced according to the absorption of the surface. And that means if you look at the right-hand figure, you can create a decay curve where you, for every time step, add up all the remaining energy in the particles at that particular time delay from they were emitted. And that works quite fine in any geometry and also with a very different absorption coefficients in the room. So this principle is a very big advantage to the Eyring and the Sabine equations, where you actually have assumed same absorption for all surfaces. And normally the interesting cases are when you have very unequal absorption. For instance, a classroom in a school with absorbing ceiling and reflecting walls. But this kind of particle model will compensate for this and give you a decay curve, and from the decay curve then you can establish or you can estimate reverberation time exactly as you do from a measurement. To the right is shown particles emitted from the source, just a few of them. And to the left are shown rays representing the path of the particles. So that's how you can see particle tracing and ray tracing, they are very similar. It's just a matter of how you look at it. If you actually follow some small patches of energy, then I would call it a particle tracing. And then we have a ray tracing method where you can follow a ray, and we need to follow the ray up to quite high reflection orders to have sufficient number of reflections for establishing the impulse response in the room. I have used here a model of the concert hall as an example. And here I have shown what is in the ODEON model for calculating the late reflections. It comes from ray tracing, but then each reflection of the ray is assigned a kind of secondary source. That means there will be a certain amount of energy assigned to each of these red spots. And you can imagine if you have several thousand of rays and each of them with maybe 100 reflections, there can be really a large number of secondary sources covering virtually any surface in the room, but with different time delays and with different energy to be radiated. And then The next step in the calculation method in ODEON is that we select the receiver point, or we could have several different receiver points, but the idea is that a receiver point will collect the energy from the visible image sources or secondary sources only. So those are not visible from a certain point will not contribute. But the visible points contribute with the proper time delay and energy. So that's how we can calculate quite accurately the late part of the impulse response. The image source is used also in ODEON, but combined with some scattering. So in addition to the specular sound, according to the image source method, we can also distribute a number of secondary sources on each surface. And then the amount of energy coming from these distributed secondary sources depends on the scattering coefficient of this surface. So we have a reflection which has the right amount of direct specular reflected sound and scattered sound. For the early reflections, in this case shown up to the third order reflection, the image source method allows us to show the reflection path between source and receiver. And each reflection path corresponds to a line in the reflectogram here in the left side, which is a very good tool to analyze early reflections in a room. And now the case is that in the computer model, we have all the information about the angle of incidence of each of the reflections. And that holds for all reflections in the impulse response, early and late. We know all the time from which direction this energy arrives, which means we can actually convert the impulse response in the receiver point to a two-channel impulse response if we use the head-related transfer function. The head-related transfer function, HRTF, gives a relation between the reflection in a certain point in the center position of the head and the result that would arrive at the two ears. And in this example, the head-related transfer function corresponds to a single reflection coming from the left. And to the left ear, shown with a red curve, we have then a certain level of the reflection. You can see in mid-frequencies around 1 kilohertz, it is with about 6 dB above the level of the reflection in the reference point without the head. In the right ear, the green curve, the sound arrives a little later, and it is attenuated at the high frequencies. So here are several things. Here are different levels, here are different time delays, and here are we can also see different fluctuations at the high frequencies. And all this information are the necessary and also sufficient information to create a three-dimensional imagination of the sound. So that's used for auralisation. And for auralisation, we need some sound recorded in an anechoic room. That means at least without disturbing reflections. Just the sound without any reflection. And then we have the calculated binaural impulse response corresponding to the room model we have simulated. And if we combine that with a convolving process, we get the auralisation. That means as this sound source would sound if we listen with two ears in this particular position in this particular room model. And the room model here is the model of the concert hall you saw a minute ago. Now, the recording is with a trumpet. This is the calculated binaural impulse response. And then we combine. Now we have a little reverberant sound added for each part of the sound. Speech in room. Well, I should like to say something about vocal communication and ambient noise. And actually this was from the EuroRegio acoustic conference in Ljubljana earlier this year. Just to give an idea of what we're talking about. What makes speech particularly interesting is the fact that we can speak with very different levels. The speech level is normally referred to as the sound pressure level in a distance of 1 meter in front of the mouth. But you can see on this curve we can have examples from around 55 decibel, which we could call relaxed, to 60, which we could call normal, to 66, called raised, or 72, called loud, etc. A wide range of output from the speech. And what is then interesting and found very early, I think in 1909 approximately, it was described by a physicist called Lombard, that if we have a certain noise level in the ears, then we automatically will raise the voice. So as a function of the ambient noise level, we can approximately estimate the level of voice we will use if we are in a discussion. I tried to look at that recently and found that although you could say it is some kind of iterative process, actually it's just to put up a few equations and they can be solved. Then I compared to a number of measured, well-documented cases, and it was realized that the Lombard slope is around 0.5, which means if the noise level increases by 1 decibel, the speech level will go up by ½ decibel. This is quite accurate according to a large number of data I have collected and compared to the model. So the simple model in the bottom here says that the noise level, if a lot of people are in the same room and if they are talking and having a good time, then the noise level will be 93 decibel minus 20 log the absorption area in the room divided by the number of speaking persons. Very simple. We can test it later on outside. However, what is particular with speech in relation to noise here is that if we can do some acoustic treatment to the room, for instance, make half the reverberation time by doubling the absorption area, then we will gain a reduction of 6 decibel. Normally, we could expect only 3 decibel reduction if we double the absorption area. But this is because of the Lombard effect. You could also say that if you double the number of speaking persons, if more people join the party and more people talk at the same time, then if you double the number, then you will have increased the noise level by 6 decibel. And here is one of the cases where this model was compared to measurements. You have a different number of people in the food court. The volume is more than 3,000 cubic meter, 0.9 second reverberation time, empty state. And then people from 150 to more than 500 persons. Well, the problem with this noise from speaking people is that we don't really know how many of the people are talking at the same time. It can, well, be very different depending on well, the situation of which people and, well, there are many things involved. But I found for most restaurants, bars, eating establishments, there's a group size around 3. That means if we know the number of people, we just can divide by 3, then we have approximately the number of people talking at the same time. And that we can use for the equation. But there can be other more dead gatherings where people don't want to talk very much, and then of course we have a bigger group size. So this model can be used also to say something about which absorption area we should recommend if we want to have a reasonable signal-to-noise level to give conditions for a good, relaxed conversation during the meal. Speech is also a nuisance in open plan offices, and here I will just briefly mention that some work is going on in ISO. There is part 3 coming to the ISO standard 3382, describing a method for open plan offices based on the speech transmission index. But here the aim is to design the office to get as low speech transmission index as possible between remote positions, because if people hear each other too clearly in this office, they will disturb each other. So we are talking about distraction distance and a privacy distance, both defined from the speech transmission index as a function of distance. So if we have measured this STI in different distances and can create curves like this, then we can estimate this distraction distance and privacy distance. And one of the good things or interesting things in using the STI for this purpose is that STI involves the background noise as well as the reverberant field in the room. So both reverberation time and background noise goes together into this measure. And this is very relevant for open plan offices because both can be used to improve the conditions. Music in rooms. Well, I could talk very long about this, but I have to make it short today. And I will now just focus on what has been made recently in connection with ODEON simulations. Namely, that we have had the opportunity to make recordings of several orchestra pieces, but recorded with each single instrument at a time. And then they were synchronized, and then we can put all the instruments in the computer model to create our orchestra, and then well, adjust the balance and listen to the total result. That is a way to solve the problem of an extended sound source like a symphony orchestra. It's not a point source. And it solves the problem of different directivity of the different parts of the source. But it is a big amount of work to do it, of course. For room acoustic and music, there's another part of the ISO standard that has established the room acoustic parameters, which describe the level, the reverberance, the clarity, the appearance source width, and the listener envelopment with one or several parameters for each of them. But back to the orchestra simulation, we have tried that with many different concert halls in the ODEON models today. What I should like to use as my example here is the new concert hall in Copenhagen, designed by Jean Nouvel, and with Nagata Acoustics as responsible for the room acoustics. You can see the data here, 1,800 seats, 28,000 cubic meter. Reverberation time with the audience about 2 seconds at 1 kilohertz. Well, it has changed last summer because there were some adjustments made, but these measured results have been kept as a secret for a long time, but we just heard at the conference recently from Nagata Acoustics that it is about 2 seconds, which is a little in the short end for this design, this volume, and that's why there have been some adjustments. So today it may be more reverberant. Anyway, we will listen to a simulated example of Mahler's Symphony No. 1, first movement. And it means that we will have a very big orchestra, 95 instruments. And you can see here in the table, we have chosen 16 first violins, etc., 8 double basses. According to the score, there must be 4 flutes, 4 oboes, etc. 7 French horns. Yeah. Okay, we have the recordings from each of these parts. Only for the strings, we don't have every single player recorded separately. For instance, we had 2 violin players playing the first violin part. So even if we have put 16 sources to play the first violin, they actually just play 2 different recordings. So it's not perfect, especially for the strings. There could be some improvements made. Anyway, I will give you some examples of how it could sound. Here you can just have a look into the computer model, and you can see all the 95 musicians now located on the stage, ready to play. And first we will listen from a position which is up here. And next we will move to a position over here on the side. I'll stop here, just to give you an idea of what is possible. We will move to the other position on the side, and since this is so complicated, there are so many instruments playing, I think for the next example, I will just play the brass group. well, I can stop here. Because now when we have just a few instruments, we have much better opportunity to hear the reflections in the room, and you can hear the reverberance of the room. But I could play, well, for very long with this because it's so funny to try to combine different instrument groups, and well, there are so many possibilities with this. But for a designer, I think this also offers the possibility to actually evaluate things like balance between the orchestra parts, comparing different listener positions, something you could not have done before without real directivity of all the instruments and real location of all the instruments. So it may have some interesting possibilities for well, better design, better evaluation. I will just mention here that these recordings were made by some colleagues in Helsinki, and we have very good cooperation with them. We made other recordings here at DTU. So there are in total 6 different orchestra pieces where we have this kind of single instrument recording. The directivities were measured by Philip Otondo in another project we had at DTU, and I got this ODEON model of the concert hall from Anders Gade. So I am now going to conclude this talk, and I just will make it very brief and simple. First, I will say that particle tracing and ray tracing are very efficient for room acoustic simulations, particularly if combined with wave-based models for scattering and diffraction. And I would also say that there is a need for good wave-based simulation models for small rooms and low frequencies, and some promising results have appeared with, for instance, the finite difference time domain method. But it's no secret that the small rooms and the low frequencies are well, difficult to model with the technology we have today. So this is one of the things we are addressing, and hopefully in the future we can also offer better models for that. Okay, thank you very much for your attention.